Assalamu alaikum. Hello, everyone. Today we will continue the lecture of basic statistics. This is the last part. So we start by talking about how to compare distributions. So the idea here is to check if two distributions are similar or not. So often there is a need to compare different distributions to derive some important insights or make decisions. What do we mean by that? So sometimes you have like access to a random variable. So when we say a random variable here, so if you have an attribute that can take different values to different records, then these values are can be considered. In fact, this is a random variable because for different records, it takes different values and it follows some underlying distribution, which we don't know, but we can actually look at those samples and try to see if there is a similarity between the distribution of these samples and for example, one of the well-known distributions like the normal distribution or the uniform distribution, whatever distribution is. So we have access to these samples. Okay, they are samples from a random variable, which we don't know its actual distribution, but from these samples, we are trying to estimate the distribution and see if it's similar to any of the well-known distributions like the norm, for example, the normal distribution or the uniform distribution. Okay, we can do one way to do it. Naive way is to actually plot the histogram. Okay, plot the histogram and look at the histogram. Okay, and in fact we did it. If you go back up in the in this file, for one variable, we plotted the histogram, and visually, we concluded that this looks very close to a normal distribution. But that may not always be a practical way to do. We can also look at the box plots. For example, if I have box plot is useful when we want to compare two variables. We have two random variables, and we want to compare them, look at them like aside to each other and see if there is similarity or not. So then we can plot the box plot of the first random variable and the box plot of the second random variable. And we look at them, we see if there is a similarity or not by looking at the different metrics. For example, the box plot, the good thing about box plot, if we go back here, if you remember here, so we have the positions of the lower and upper whisker limits, the lower and upper quartiles, the median. So we can, if we have two box plots, then we can look at them like aside of each other and see if there is similarity, if the positions of these are same or not, or if there are differences. Okay, by visually looking at these box plots, we can tell if there is similarity or not. But there is also like a more theoretically rooted way to do this, to test, like if two random variables are similar, or if a specific random variable is following a certain distribution. So this is what we call hypothesis testing. Okay, so in hypothesis testing, we actually claim something and then we test it. Okay, and based on the value of the confidence or the probability value, which is the return of the testing, we can conclude. Okay, so we can actually reject the hypothesis that we bought, or the claim that we stated or accepted. Okay. Okay, so here is more information about this hypothesis testing. So I have a hypothesis is a way to state our assumption or belief that could be tested. So we state an assumption, a claim, a belief, okay, that can be tested. Okay, the default knowledge or our claim, okay, our claim will be, or our assumption will be the null hypothesis. It's called the null hypothesis. Our claim is called the null hypothesis, and the opposite of this claim, or the opposite of this default knowledge or assumption, is stated as the alternative hypothesis. Okay, for example, here we can have, like, for example, the null hypothesis is no difference between the two distributions. So we are given two random variables, and we are claiming that there is no difference, there is no difference between their distributions. That's our null hypothesis. That's what we're going to test. Then the alternative hypothesis is the opposite of that, which is there is a difference between the two distributions. Okay, so then what's the probability value, which is the return of the test? The probability value is a confidence or a probability value of the null hypothesis. Think of it as the probability that what we believe or what we claim is equal to that. Like, it's the probability of that. So if it's high, then our claim seems to be a correct claim. If it's low, below a certain threshold, then we will actually tend to reject it. Okay, so it has a low probability, so we will not accept it. Okay, it indicates how much we believe, sorry, it indicates how much we believe the two random variables are the same, okay, for that specific case or scenario or example, but it's more general than that. It depends on the test, actually, okay? Something happening with my, okay. If B is very small, then we can reject the null hypothesis and accept the alternative hypothesis. Okay, I don't know what's happening with the computer. Let me clean this. Okay. Okay. If the probability value is very small, okay, if it's lower than a certain threshold we put, then we reject the null hypothesis and accept the alternative hypothesis. So we don't. So if the value of p, if p value is small below a certain threshold, then we reject the hypothesis and we accept the alternative hypothesis. However, if p-value is not, if p-value is exceeding that threshold, okay, it's not very small, then we fail to reject the null hypothesis. We don't say we accept the null hypothesis, okay? We just say we fail to reject the null hypothesis, okay? So the probability has exceeded that threshold, okay? So we just fail to reject it, okay? So it could be weak accept, could be, depends on the value of p, okay? But yeah, in other words, when we fail to reject, then we kindly of accepting, okay? But statisticians are like uh, very careful with the use of wordings, okay? So we fail to reject it because the probability exceeded a certain threshold. But then how confident we are about that claim, that's reflected by the value of P. If P is very high, for example, if P is equal to 1, then we are sure that, yeah, the probability is so high, so we tend to strongly accept it, okay? But if P is very low, close to the threshold, then we just fail to reject the null hypothesis, but the probability is maybe is not, yeah, it's a, think of it as a weak accept or fail to reject, in other words, okay? So typically the value, okay, so this is a typical value. I would say the exact value depends on the application or the use case, but the typical value that is used is 5% or 0.05. So if p-value is less than 5%, then we reject the null hypothesis and accept the alternative hypothesis. If it's greater than 5%, then we fail to reject the null hypothesis. So here are some typical tests we perform. The first one is Shapiro-Wilk test. Okay, we test if a data samples follow a normal distribution. So then the null hypothesis is that the sample has a normal distribution. Okay, then the alternative hypothesis is that the samples do not follow the normal distribution. So we have also students t-test. This tests if the means of two independent samples are equal. So the null hypothesis is that the means are equal. Okay, but there's an assumption here. Okay, students t-test assume like these samples are coming from normal distribution. Okay, so there is an assumption that the underlying distributions of these two independent samples is the normal distribution, and the null hypothesis that the mean of these two samples is equal. Okay, the means are equal. The alternative hypothesis is that the means are different. Same thing for Mann-Whitney U-test. It's the same null hypothesis. The means of the distributions or the samples are equal. Okay, but it doesn't impose the assumption that these samples are coming from the normal distribution. Here we will work with this example. We have two variables, okay? And we're gonna check if score 1 and score 2 follow the normal distribution. And then we're gonna draw the box plot for both of them to just visually compare them, compare their similarity and dissimilarity. Then we will check if the means of score 1 and score 2 are equal using student's t-test. And then we're gonna check if the means are equal using the Mann-Whitney U-test. There's something I would like to mention here. So now we're gonna first check if score 1 follow the normal distribution or not, and then we're gonna do the same for score 2. Now, if one of them doesn't follow the normal distribution, then the result of this student's t-test will be misleading, right? Because the student's t-test assumes that the underlying assumption of these two independent samples is a normal distribution, right? So now if one of them doesn't follow normal distribution, then we shouldn't be performing student's t-test, right? Because it will be misleading. So if you want to perform student's t-test to check if two random variables are coming, if the means of two random variables are equal, then you first need to perform the Shapiro test. Oh, sorry, without naming it now, we didn't come. Yes, we will perform the Shapiro-Wilk test first to see if they both follow normal distribution or not. And if they both follow the normal distribution, then you perform the student's t-test. Otherwise, you don't perform the student's t-test, you perform Mann-Whitney test, okay? Because this doesn't impose the assumption that they are coming from the normal distribution, okay? So here we define score 1 and score 2. We are importing NumPy as MP, and in fact, we didn't use it here. We pass the list. So this function Shapiro takes a list as an input, okay? So these are two lists, okay? A list contains the first list score 1 contains the first random variable and or data, okay? Or the values for this attribute score 1, and the second list contains the values for the second attribute score 2. Here we from scipy.stats we import Shapiro, and things after that are very simple. So we call the function Shapiro, we pass score 1 as an input, and we return two variables. For now, we focus in the p-value. That's what we care about for this course. The probability value, okay, which is the second return. And then we just want to add this condition here. If p-value is less than 0.05, then we reject the null hypothesis, okay? So then we say this doesn't follow the normal distribution. Otherwise, we fail to reject it. As I said, we say here, we fail to reject the null hypothesis, okay? We did it for score 1 here. We do the same thing for score 2 here, okay? And that's what we get here. Let's see. Score 1, oh, I didn't run this cell. Okay, let me run this first. Okay, now we run this. So the value here for the first one is 0.29. So it's greater than 0.05. So we failed to reject the null hypothesis for score 1. Here the value is 0.012. So it's less than the 0.05. So we reject the null hypothesis for score 2. So in other words, score 1 follow normal distribution, but score 2 doesn't. Here we plot the box plots for both variables, okay, to look at them visually, okay, beside each other. So let me do it this way here first, and then we'll come to this. So simply, we import the required library. We here create the figure, okay. So we are importing matplotlib.pyplot as PLT, and then here this line, we already explained this in the past, okay. This line just creates the figure with this size we are passing here. So here we are defining two subplots. This is the first subplot, okay, axis 1, fig.add subplot. So we're saying like there's one row and two columns of subplots. So there will be two subplots in a row. Okay, and this subplot is the first one of them because there will be two. Here, it's one row of subplots and two columns. So there will be two subplots in one row. And here we're defining this as the first one of them. Okay, And in that, here we do here where the actual plotting is happening. So we call the function box plot. Okay, so ax1 dot box plot, and we plot score 1. So in the first subplot, we are plotting score 1, and then here we're accessing the second subplot. So again, so we have one row, two columns of subplots, so two plots in one row, and we are accessing the second one. Okay, that will be the second subplot we will be using, and in that second subplot, we are plotting score 2. Okay, and then we are adding a title here and showing the plots. So if you run this is what we get. These are the two subplots. Okay, so here, though we are defining a subplot, but actually it's only one subplot here. Okay, so we're creating the figure, and we are defining only one subplot. So the number of rows is 1, number of columns is 1. So there's only one subplot, and here is the position of the subplot, which is the first one. It's the only one here, and we are plotting the box plot of these two variables aside, like beside each other. Okay, and then we're adding a title, and we're calling this function set xtick labels score 1 and score 2. It's gonna add labels at the x-axis. So that's why actually we created the subplot here, so we can access this function and add these labels in the x-axis. So if we run this is what we get. Okay, let me make the size smaller here. This is too much. Okay, so we can look at them. We do this. Okay, still high. Oh, here. Yeah, this is it. You see, score 1 and score 2. So by looking at these two box plots, we can see that there are so many differences, right? Like for example, here the lower quartile of this one is below even the lower whisker limit of this one. And so yeah, you can look at this, and there are many differences. This is more scattered inside the without having outliers. Okay, but here there are outliers because it's more the distribution is more, most of the samples are more around this, and there are like these two outliers. But here the data is more scattered without like outliers. There are no points after the upper whisker, and in fact this point may not even exist, by the way. Okay, yeah, anyways, looking at these two box plots, we can tell like there are many differences here. Okay, so now we come to the student t-test. Okay, we import this function here, t-test underscore end from the scipy status, from scipy.stats, and then we call this function here. We pass now, because we are testing if the means of these are equal, so we're passing score 1 and score 2. And here there's another argument we pass here. So we're saying that equal var is equal to false. That means we don't assume that they have equal variance. Okay, the default choice, I think the default option for this is to be true, but here we're not assuming that. Okay, they do not have the same variance. And yes, with that, yeah, we check the condition. So again, student t-test here will be misleading because actually one of them doesn't follow the normal distribution, but we are running it anyways. So now we got this result, so 0.15. So then it's greater than 0.05. Then we fail to reject the null hypothesis. So we fail to reject that their means are not equal. Okay. Okay. So yeah, so that's the way you interpret it. So even if we do this, let's do this true. Okay. Okay, the difference is not that much. That one was, I think, 1.156, and this is 0.155. So we failed to reject the null hypothesis. Okay. Okay. So more correctly to do it is with Mann-Whitney test here, because they do not follow this one. The second one, we actually rejected the hypothesis that it follows the normal distribution. So they may have different distributions. So we run this test here, the Mann-Whitney. So we need to import it here as we can see, and then we just call it and pass score 1 and score 2. Okay. So 0.059. It's very weakly, like very weakly accepted, I would say, because it's we failed to reject it. We failed to reject it, but we are at the very like at the boundary. Okay, we are slightly higher than 0.05. We failed to reject the null hypothesis, which is the means are equal. Okay. With that, we come to the end of this topic. I just want to mention two things. I want to go back. I forgot to do it at the when I was talking about here. So here we used Python to find Q1 and Q3, right? And if we print them out, okay, score is not defined. Okay, let me, before we print this out here, this is using Python, but actually if you look at data, okay, so what if you are asked to find them from the data here? Okay, Q1 and Q3. Okay, these are 25 elements. This is the one in the middle. This is the 13th. Okay, so then look here, 50% of the data is below this one. That means half of the samples below this one, 12 samples, and half of the samples are above this one, the other 12 samples. So from the beginning to here, to the median, there are 13 samples, right? There are 13 samples. Then the seventh one is the lower quartile, or the 25 percentile, because that is the half of the distance. Okay, 25% higher and 25% lower from the first half. So it's the seventh one, right? It will have 6 below it, 6 samples, and 6 above it, including the median. So let's count that. 1, 2, 3, 4, 5, 6. It's the seventh one here, this one. There are 6 below and there are 6 above. 1, 2, 3, 4, 5, 6, including the median. So this one is the 25 percentile. 25% of the data is below, 6 samples are below. Okay. Now we also include the median in the second half. Now we have 13 samples here. Okay, then the 75% is what? Is the half of this distance. So then 13. So then we go 6, right? And it will be the seventh one. 1, 2, 3, 4, 5, 6. This one, it's the seventh one. Because this is half of the data. Okay, half of that will be the half of this will be this is 50% of the data, so half of that will be 25% plus the 50% we already have below this. That's 75%. Okay, so 1, 2, 3, 4, 5, 6. The seventh one, it's this one. 6 below it. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, it's this one. Okay, only 25% of the data is higher and 75% of the data is lower. Okay, that's one thing I wanted to mention. There's also, I was watching the recording I did for this part here. Okay, here, this part. So as I said, so I explained that very well, like that. This is, I hope it was very well explanation that we're dividing by n minus 1. So with that, we are actually producing the unbiased estimate of the actual or the population variance. Okay, so it's a sample variance, but unbiased estimate. I've been saying that many times, but in one of the times at the end, okay, after I went back from the example that I show for the mean, I said when we divide by n minus 1, we produce a biased estimate. No, I meant when we divide by n, we produce a biased estimate. When we divide by n minus 1, we produce unbiased estimate. So this is unbiased estimate of the actual variance. Okay, so I was showing the example for the mean. So the mean, when we consider n at the denominator, so for the mean we have sum xi over small n, right? That's unbiased estimate of the actual mean. Okay, but if we do the same for the variance, if we divide only by n small, then there's a long proof, okay, that shows that's a biased estimate. We have to divide by n minus 1 in order to get unbiased estimate. So I showed the simple proof for the mean. Okay, just to explain what do we mean by unbiased estimate. That was for the mean because the mean was simpler proof to do, but for the variance it's a longer proof where we're not going to go to that level for this course. So but simply if we divide by n small, then we produce a sample variance, but that variance will be a biased estimate of the actual variance. So if we want to get unbiased estimate, then we need to divide by n-1. So this one we see here is a sample variance that's unbiased estimate of the actual or the population variance. With that, we come to the end of this topic. So in next lecture, inshallah, we will start a new topic. And thanks for watching.